Hi there and welcome to Hegarty Maths. It's Mr. Arnold here, and in this video we're going to take a look at the second derivative and also a few varying problems on how to use some differentiation or applying differentiation. Now this video is geared towards A-level maths but is applicable to most other maths modules. So let's just take a look at the second derivative. So suppose we've discussed the idea of y being equal to some function of x, and that if I take the derivative of y, if I get dy by dx, we get the rate of change of y with respect to x, or in other words f dash x. So we can take the derivative using our rules from before and get dy by dx, but that's what we call the first derivative. We can actually continue and work out the rate of change of the gradient function. So this function here tells us the rate of change of the function. So the rate of change of the function, or a function, sorry, I beg your pardon, this tells us a function for the rate of change of the function. Bit of a mouthful there. And the second derivative, sometimes referred to as d2y dx squared, or f double dash of x, tells us the rate of change of the gradient function. So this tells us how much is the gradient function changing with respect to x as we change x. So the rate of change of the gradient function. And in theory, you could go on, you can get the third derivative and so on and so forth, and you can actually find many different types of derivative, but you will find that in mathematics we tend to use the first and second derivative more than anything. So let's just take a look at how we might find the second derivative. I've got a function here, y equals 4x squared, subtract x plus 3. I'm asked to find dy by dx and d2y dx squared. So what I'm going to do is first of all find dy by dx. So using our rules from before, power down in front multiplied by coefficient gives me 8. Reduce that power by 1. Derivative of minus x is minus 1, and derivative of a constant is 0. And then if I want d2y dx squared, we simply take the derivative of the derivative. So the derivative of 8x subtract 1, derivative of 8x is just 8, and the derivative of minus 1 is 0. So that's the second derivative. Let's take a look at another example. So I've got y equals x cubed plus 5x squared plus 2x subtract 6. So let's get dy by dx, and that will give us 3x squared plus 10x, so remember power down in front by coefficient, plus 2. So we get a quadratic function, and then to get the second derivative, d squared y dx squared, or d2y dx squared, we just take the derivative of this. So 3 times 2 is 6, drop that power by 1. 1 times 10 is 10, drop that power by 1, we get x to the power 0, and the derivative of a constant is 0. Another example, so we got y equals 3x to the 6 minus 4 all over x squared. And you may remember from the last video, when I've got something like this, it helps me to split it into two fractions. So 3x to the 6 over x squared, subtract 4 over x squared. I'm going to try and write everything in index form in one line. So x to the power 6 over x squared is x to the power 4, so we get 3x to the power 4, and then I can bring this x up and change it to a negative 2, so minus 4x to the negative 2. Okay, now we're going to differentiate. So dy by dx will equal 4 times 3 is 12, drop your power by 1 to a 3. Negative 2 times negative 4 is positive 8. And remember to drop the power by 1. And then now we're going to go to get the second derivative. So the derivative of the derivative. 3 times 12 is 36. Drop that power by 1. Negative 3 times positive 8 is negative 24. And then drop that power by 1. And job done. And the final one. Oh, that was the final one, I beg your pardon. We're going to do a couple of problems next. In the next video, we're going to actually look at applications of the second derivative and how we find it useful. So, and that's actually for core 2. But for now, let's have a look at some applications of differentiation. So, suppose a ball is thrown vertically downwards from the top of a cliff, and the distance s in meters of the ball from the top of the cliff after t seconds is given by s equals 3t plus 5t squared. Find the rate at which the distance of the ball has travelled is increasing when t equals 0.6. Okay, so the key word here in this question is the word rate. And when we see the word rate, that means we're going to differentiate. So if I take the function s equals 3t plus 5t squared, and I find the rate of change of the distance, or ds, with respect to the time, dt, so differentiate with respect to t, we get 3 plus 10t. So it's exactly the same as if I was differentiating y equals 3x plus 5x squared. So nothing has changed, it's just that we're using s as s and t instead. So ds dt equals 3 plus 10t, and I want to know, well, what is the rate when t is 0.6? So what we do is we evaluate ds dt, evaluate that when t equals 0.6. So we get 3 plus 10 times 0.6. Well, 10 times 0.6 is 6, plus the 3 is going to give me 9, and it's in meters, so it'll be, and s is in seconds, so 9 meters per second. So after 0.6 of a second, the ball is traveling at 9 meters per second. Okay, what will the rate of change be, or what is its speed, in other words, when the ball has travelled 54 meters? So what I need to do is substitute the 54 into the original expression. So we get 54, or the original equation, 54 equals 3t, this is part B, and that was part A, 3t plus 5t squared. I see a squared term, a power of 1 and a constant. Looks like a quadratic, so I'm going to write it in the form of a quadratic. 5t squared plus 3t subtract 54. Okay, and that's equal to 0. So what we're going to have to do is factorize this. Well, we're going to have 5t in both. Now I'm going to do a slightly shorter version of factorizing. No, in fact, let's do it the long way. Let's do it the long way just to make sure. 5 times negative 54 is negative 220. I think 5 times 5 is 25. 250, 270 should I say, 270. 270. So we need two numbers that multiply to make 270, but need to add to make positive 3. Okay, numbers that multiply to make 270 but add to make positive 3. Okay, so with a little bit of thought, numbers that multiply to make 270 but add to make 3, I got 15 and 18. So 5t squared, it's going to be negative 15 and positive 18. We have that 54 at the end, equal to 0. So I've split this negative 15 and positive 18 will give me that positive 3. Factorise by grouping, I can factor out a 5t here, and that leaves me with t minus 3. And I can factor out, let me see, 18. 18 will come out and leave me with t minus 3. That must be equal to 0. So we get 5t plus 18 times t minus 3 must be equal to 0. And what are the options we have? T could equal 3, or t could equal negative 18 over 5. Well, we can't have a negative time, so it can't be that. So we're looking at when time is equal to 3. So what is the derivative when t equals 3? So I need ds dt, ds dt evaluated after 3 seconds. So ds dt after 3, we get 3 plus 10 times 3, which equals 33 meters per second. A little bit of an application there. Remember, when we take the derivative, it's like finding the rate of change. Okay, next example here. Water is poured into a vase such that the depth h of the water of the vase after t seconds is given by h equals kt to a third, where k is some constant. Given that when t equals 1, the depth of the water in the vase is increasing at the rate of 3 centimeters per second. Find the value of k. In other words, it's telling me that dh, the change in depth with respect to time, equals 3 when we evaluate at t equal to 1. Because it tells me that when t is equal to 1, the depth of the water in the vase is increasing at a rate of 3 meters per second. So the rate of change of the depth with respect to time is 3 when t equals 1, when we evaluate at t equal to 1. So see if we can work out k now. H equals kt to the power of a third implies dh dt. So let's try and take the derivative. Well, it's going to be 1/3. So the power of t multiplied by the coefficient, which is k, 1/3 k. Reduce that power by 1, negative 2 over 3. Right, so this here is going to equal 3 when t equals 1. So let's see if we can fill that information in. So we get 1/3 of k times 1 to the power of negative 2 over 3 will equal 3. Well, 1 to the power of negative 2 over 3 is 1. So, and when we cross multiply by 1/3, we get k equals to 1. Multiply both sides by 3. This value here ends up being 1, so k is going to equal, not 1, 9. Sorry. If I multiply both sides by 3, we get k times 1 to the power of negative 2 over 3 equals 9. Hence, k must equal 9. Okay, now that we know that k is 9, find the rate at which h is increasing when t equals 8. So, now that we know k, let's rewrite dh dt. So we know what k is. That means that dh dt equals 1/3 times 9, which is 3. 1/3 times 9, which is 3. T to the negative 2 over 3. So that's the new or an updated version of the rate of change. Well, we want to know what the rate of change is when t equals 8. So now we need to evaluate dh, dt. We're going to evaluate after 8 seconds. And that will equal 3 times 8 to the power of negative 2 over 3, which is going to be 3 over 8 to the power 2 over 3, which is 3 over 8 to the power of a third squared. So I'm using my laws of indices here. 2 over 3 can be split into 1/3 times 2. So I'm using that law that I know, which gives me 3 over, and 8 to the power of a third is 2, and so we get 3 over 2 squared, which is going to be 3 over 4. So the answer is 3 over 4 centimeters per second. 3/4 of a centimeter per second. Okay, one more example today, one more problem. So we've got the line with equation y equals 2x plus k, and it's a normal to the curve with equation y equals 16 over x squared. We're asked to find the value of the constant k. Right, so we've got this equation here, and it's a normal. It's a normal to the curve. That means it's related to its tangent. Let me see, the gradient of this line up here, the gradient of this line equals 2. So that means the gradient of the tangent must equal the negative reciprocal of this. The normal and the tangent are perpendicular. So the negative reciprocal must be negative 1/2. So that's the gradient of the tangent to the curve. Okay, so y equals 16 over x squared. Let's write that down now. Y equals 16 over x squared. Well, what is the gradient function for this? Let's get dy by dx. In order to get that, I'm going to rewrite this as 16 x to the minus 2. So dy by dx equals negative 32 x to the negative 3. So negative 32 x to the negative 3. So the gradient of the tangent where it meets this particular line is negative 32 x to the negative 3. Let's see if we can work out what this point is. So negative 32 x to the negative 3 will equal negative 1/2 somewhere. The gradient, this is the gradient function, it's going to equal negative 1/2 where this normal is. So I'm going to multiply both sides by negative 2, and we get 64 x to the negative 3 will equal 1. Divide both sides by 64, we get x equals negative 3, x to the negative 3, sorry, over 1 over 64. So x to the negative 3 equals 1 over 64, which means that x to the 3 will equal 64, which means that x, what is the cube root of 64? It's got to be 4. So when x is 4, we get a particular value for y, and that should match this. So the the equation of this line will meet this curve here when x is 4. So let's work out what the value of y is. So y will equal 16 over, now we're letting x equal 4, so you get 4 squared, so y equals 16 over 16, so y equals 1. So this particular line will meet this particular curve when x is 4 and y is 1. So let's see if we can work out what k is. I'm going to substitute 4 and 1 back in here, and then that should give us a value of k. So we get 1 will equal 2 times 4 plus k. So we get 1 equals, it's a shocking looking k, let's make that look like k again, 2 times 4 plus k. 2 times 4 is 8 plus the k. So we get that k will equal -7. K equals -7 for that particular problem. Okay, that's it from me. Hopefully you found this useful. Be back again with another video soon. All the best.